Okay, so Jason has had similarly bad luck with transportation. And he hopes to be here for dinner, we think. Maybe? He hopes. But he's supposed to be on his way, so you can certainly talk to him about this paper throughout the week. Yes, apparently we know he's gotten that far. So I've decided to be kind because I think this is work that should be looked at and discussed. Caveat, he didn't make this talk. All of the code, however, is from his paper. But I have not written this, so we'll hope that I can get through this. And you can certainly ask him later. So this is deriving pure naturally recursive operations for processing tail-aligned lists. And before we get going, anyone know why I can't find the top of Dr. Rackett's stuff? Oh, there we are. Hide interactions. So before we get too far into things, Jason, at the first of his paper, suggests that we consider how to write a function to compute the lopsided longest common suffix of two lists, and how to write the longest common suffix. Now, we don't want to write these just naively, because we'd like to get good performance. So, we take a moment and think about how we might do this. We could probably come up with implementations, but he's trying to come up with a nice, reusable, flexible, good computation, and readable definition. So, let's start simpler, though. Oh, sorry. Through this work, they're presenting a pattern of programming over tail-aligned linked lists to where you can not worry about the fact that it's the wrong way round for how we normally think about things. We're good at thinking about prefixes on lists. This is suffixes on lists. And we know that there are no sharing amongst the lists. They're non-circular but finite. They don't know how long they are. And we don't want to pre-compute anything about the data in these lists. All right, so if we start simply, we can first think about how would we write a largest common prefix of two lists. We've all probably done this in our first course, or our first functional programming course, simple code. So we have least common prefix. Are the two lists empty? If not, see if the fronts are the same, go on. So we can use that to write our first iteration of least common suffix. Turn the lists around, find the least common prefix, turn that around. Simple, easy, but not very good performance. If these lists are very big, that's bad. All right, so let's start thinking, well, we can do a little bit better. We know how to do things better. We can just use an accumulator. Gets rid of one reverse. But we still have to essentially turn the lists around in order to start thinking about this. Okay. So let's simplify the problem from a first approximation. Let's consider the case where we know that the shorter list is given to us first. Okay, so what we can do then is we can walk down the list, the first list primarily, until we get the first list to be empty. And then we use continuation passing style to say, we've got to the end of the first list, so we should start now looking back at what were the lists that we saw, elements that we saw leading up. So we've walked to the end of one list, storing up what we're going to look at, and we can now see, these are the elements of the list we need to look at until we hit the difference. So we've only had to walk one length. Am I making sense? Okay, good. Since I didn't come up with it, I just have to remember it and understand it and then explain it. All right, okay, so that's something we can do if we get the shortest list first. not likely to know we do that. If we know this, we'd have to walk the lists, both of them already, and we've ruined any potential performance gain, since we don't want to walk the list more times than we have to. Okay. So what does this one do? So what we're trying to do is sever the connection between into and out of recursion. Trying to remember how this one is different than the previous one. I can pull it all back up. Ah, can you speak up?
Section 2, the CC, the first network LCS doesn't have the continuation possible.
Right.
So the LCS 3 should not have the argument K.
Well, I did skip one from the progression from the paper.
Just accumulating
Okay.
results. This is just we can everything one go with the J capture continuation.
Okay. So I think I meant to.
It also has a car of L2 in the penultimate line. And the second one doesn't. The one above doesn't.
Yeah, because it was capturing an additional continuation, I think.
I'm just being diff here.
Oh, that's fine. I had to do a bit of that as well. Right, so why do we not need the car here? Okay, well, the point remains. And the paper does a full progression, and I had to skip a couple of steps because there was just too much code and too much text. I didn't want to stand up here and show you the whole paper, page by page. The point is that we try to push things through the continuation so that we walk to the end of the list. So this lets us store the comparisons that we're going to do once we get to the end of the short list, which is the first list. But that's not sufficient for the case where we don't know the length of the two lists. For that, no, this one is still the short list. For that, we try to build a generalization, which is going to say, we want to be storing both lists as we walk through, so that when we hit the end of either list, we've stored a continuation of the comparisons for either side of the list. So when we get to the end of only list, we can build up the end of its list until the first of the other list. So basically, we walk all the way to the end, keeping two sets of continuations of these are the elements we need to compare, these are the elements we need to compare. We walk to the end of the other list till we get to the end of it, and then we return and start looking at all of the comparisons. Does that make sense?
So the continuations you're building don't store pairs because, of course, you're out of sync as you're walking through. So that's okay.
Yeah, so we don't store the pairs. And we know that the call CC in this circumstance is only going to be invoked once. It's only going to be invoked at the end when we're ready to actually perform the computation to see what the longest suffix is. And so it's not a heavy computational burden to have the call CC. And this solution severs the connection between several connections can list between breaking tail form. And we can then use this to solve other problems where we need to find the matching suffix of two lists. And they demonstrate this in the paper by using this to do element-wise max, following the same progression of how would you write this naively, and then how can you apply the same sort of continuations similar to this solution in order to not have to process lists multiple times. Right. So if there are questions, I can try to answer them,
Well, I'm not
but
sure if we can try to answer, but
I can try.
it is actually better form. Because basically this creates a lot of for the procedures.
It will have a lot of procedures, so it depends.
Any procedure creates lots of procedures. So if the memory allocation itself can be just moved through there,
So it will perform fewer iterations over the lists than the naive implementation. Whether or not that's going to have better performance probably depends on the overhead of the compiler for creating all of these different processes. If it's fairly low overhead for creating each of the applications, then you will have a smaller number of steps than doing an exponential pass through the two lists.
but the initial implementation costs only the ON time. Yes, the reverse one.
It's linear.
Yeah, that was linear. They discussed other implementation attempts that were not linear. So that might be a good question for the author. He has not provided performance numbers, but the complexity is you're mostly dealing here in the constant factor. So the constant factor is 3 for the naive implementation. And the constant factor here is not 3, but is related to how expensive it is to create the elements of the computation storing up. So it's possible it's better. It's possible it's worse. It might really depend on how large of a list we're talking about. I don't know if they've done much performance analysis. It's an interesting technique. Yeah, Scott?
You talked a bit about giving you a sort of computational recipe for thinking about sort of ends of lists rather than posts of lists.
Yes.
But this is not a recipe I would want to use. So do they just as a programmer, right? This is tricky code. This is a sort of easy code, like if I was trying to find the prefixes and I wrote that first thing. So do they have any comments on how one might go about turning this into more of a recipe that will let you write good, maintainable, sort of easy to understand code? Maybe some macros or something to encapsulate part of the recipe.
No, although I think that's a very good suggestion to make when they're here. I mean, they've done it twice, and the second one is easier to read having read this one. And they're very similar, so it does suggest that there is something that you could lift out into a macro or a library to make this kind of thing work with just passing in, here's the functionality I want to do over these suffixes of lists rather than building it from scratch each time. Right. Is there anything else? Good. So, thank you for coming to the Scheme Workshop this year.